Hey everyone, we're going to take a brief moment here to talk about something that we've sort of seen a little bit in this course, but we haven't really talked about in any sort of depth. The idea is the idea of work. Now, work has shown up specifically in our energy conservation equations. We've said up to this point that work is just a way that the total energy of the system can change, but we haven't really said what it is. Now, we of course know that work is not the only way that the total energy of a system can change. The other way is through heat, energy that is entering into the system or leaving the system during the process. So how are these different? Why don't we just have one piece on the right-hand side of our equation that describes the way that the energy can change? Well, for a moment, let's recap what we know about heat. An example of heat being transferred into a system is a pot of water on a stove. We say that the water has some amount of energy, and when we turn on the stove is transferring some of its energy into the water. Usually we describe this as heat, assuming the pot of water is our system. So what makes work different? Well, let me just show you an example of doing work. Let's say that I'm just holding this object right here, and then I raise it. Well, clearly the amount of energy that this object has increased. It started down here with some amount of gravitational potential energy, and now it's been lifted up here. It has more gravitational potential energy. Its energy has increased. But how did it happen? It's not heat, at least as we sort of understand heat. This is an example of work being done. So what is work? I'm going to give you a definition and then we'll dig into it a little more and see what it means. Work is a force acting over a distance. Now, this immediately begs the question, what is a force? Now, in a lot of introductory physics classes, forces is one of the first topics that is covered. We are not going to cover forces in depth in Physics 7a. You'll see them more in Physics 7b. But a force at its core is a really simple concept. It's just a push or a pull. Pushing on this bookshelf means I'm applying a force to it. When I push this object up into the air, I am applying a force to it. So what does it mean to say that work is a force applied over a distance? Well, let's again look at this object. Suppose that I'm just holding it here in the air. Now I'm actually applying a force to this object. Gravity is constantly pulling down and wants the object to fall to the ground. By holding it, I have to counteract the force that gravity is providing by providing a force of my own upwards. But there's no work being done here because the object is not going anywhere. Work requires that the object that is feeling the force is moving from one place to another. If I now push this object up, I have now done work on the object because I pushed the object up and the object has moved up. Now forces are measured in a unit called newtons, named after the famous physicist who sort of wrote down for the first time a solid mathematical description of forces. To get from a force to work, we just have to multiply the amount of force that was applied by the distance over which the force was applied. For example, let's suppose that in order to lift this object up, I have to apply a force of 50 newtons. Let's say that I lift this object up so that it is now 2 meters above where it started. I have applied a force of 50 newtons over a distance of 2 meters, the distance that I lifted the object. So the amount of work that I did on the object is just 50 newtons times 2 meters. It turns out that a newton times a meter is just equal to a joule, exactly what we expect if work is a type of energy. So the amount of work I did by lifting this object using 50 newtons of force for 2 meters is exactly 100 joules. As I said, this makes sense. In order for work to appear in an energy equation, it needs to have units of energy. It needs to be in joules. And this is exactly what we found. Now it turns out that the connection between work and energy is actually much deeper than this, but we're going to save that for a video later. For now, Just remember that work is just another way for the total energy of a system to change. In the math, it works exactly the same as heat. It just goes on the right-hand side of the equation. Up to this course, our main focus has been trying to understand how different kinds of energies change when processes happen. We look at this by trying to identify how much the total energy of the system changes. If the total energy of the system goes up or down, we know that that energy has to either come from somewhere or go somewhere. It can't just disappear. The main mechanism that we've had up to this point for doing that is with heat, energy that's just entering or leaving the system in no particular way. When work is being done on a system, that is energy that is either entering or leaving the system. Heat tends to do with internal energies. For example, when the temperature of something is being increased because energy is coming in, then in all probability, that energy is coming in the form of heat. Work tends to do more with mechanical energies. This makes sense because the example I gave only involves gravitational potential energy, which is a mechanical energy. Now we'll see a lot more about how to use work to actually learn interesting things about a system later. That's all for now. See you in the next video.